Hello and welcome to Nikolay's genetics lessons, and today's problem is your father has dominantly inherited form of retinitis pigmentosa, an eye disease that leads to blindness in middle-aged people. Now you are 25 years old and you took a vision test to check whether you are developing this disease. In 2/3 of all people of your age who carry the gene, the vision test is abnormal, while in the 1/3 it is still normal. Your test was normal. How likely is it that you carry the gene? Use Bayes' theorem in order to solve this problem, and here's 5 answers to choose from. You may take a time, try to solve this problem on your own first, and when you would be ready you can run video again and you can compare your answer with my answer and explanation. So imagine that, for example, this line represents lifetime of the person, and somewhere, say here, this person would be middle-aged and should, if he has this defective allele, his genetic disorder should manifest itself phenotypically. So at the beginning of the life until this age, say this is going to be 40 years old, this person has certain probability to develop this genetic disorder. So we can say that there are checkpoints. This can be years. We can add more checkpoints which represent months and even days. And of course, with the passing time, as you see, there is more probability that someone is not inherited this genetic disorder than probability that this person inherited this genetic disorder. And say if we would leave just 1 month or 1 day here on this time scale, it would be highly unlikely that this person has developed or will develop this last month this genetic disorder. So at the beginning probability would be higher, or likeliness would be higher, and at the end, and especially at the very end, likeliness that this person would develop this genetic disorder would be very small. So now time scale shows us that this person has much more probability that he is homozygous normal, so genotype would be small a, then likeliness that this person would be carrier, or this is we also say this is dominant genetic disorder, or his genotype would be capital A and small a. So this homozygous recessive genotype is normal, and this heterozygous genotype would be abnormal. But as you see, likeliness is different. Time have passed, and now likeliness that this person is heterozygous or carrier of this defective dominant allele is 1/3. And also what we know about father and mother of this person, we know that father is affected, so his genotype is capital A, small a, and nothing is said about his mother, so we have to assume that she is phenotypically and genotypically normal. And as you see, probability for this couple to have affected children would be 1/2. So these children would be affected, and these children would be phenotypically and genotypically normal. Now, in order to solve this problem, we need to build a table. In this table we would have 2 rows, that represent two assumptions. First assumption would be that person is carrier of this genetic disorder, of this defective allele, and the second assumption would be that this person is normal. And our prior knowledge, so prior, tell us that probability for this person to be a carrier as 1/2. And at the same time, probability that this person is homozygous normal is also 1/2, according to this Punnett square. But we also have conditional information or additional information that at the 25 years old, this person now has 1/3 probability of being a carrier. So this is conditional. And 1/3 here. And this is probability that this person would develop this genetic disorder if this person is heterozygous. But if this person is homozygous normal, so imagine that we just change this dominant allele to small allele, that means that 100% of the progeny also would be phenotypically and genotypically normal. So in this case we can say that 1/1 or just 1 would be a probability that this person is genotypically and phenotypically normal. And next row would be joint probability, so joint probability of these two events. So we have basically multiply 1/2 by 1/3 here, and we are going to get 1/6 joint probability, and in next column we have to multiply 1/2 by 1, and we are going to get 1/2 here. So let's call this probability of event A, and this is going to be probability of event B. So we have two probabilities whether this person has this defective allele or whether both alleles are normal. And next, and this is going to be our final calculation, we have to use a formula. So this is going to be posterior or final calculations in which we use formula. So joint probabilities of event A divided by joint probability of event A plus joint probability of event B. And in this column we would have joint probability of event B divided by joint probability of event B plus joint probability of event A. And of course, whatever number we are going to get here plus this number would equal to 1 or to 100%. So whether this person has defective allele, one variant, second variant, he is homozygous normal. This probability plus this probability would give us 100%. So we know that joint probability of event A is 1/6, so 1/6 divided by 1/6 plus joint probability of event B, which equals 1/2, and we have 1/6 on top, and we have to multiply here by 3, and here we are going to have 1 6 plus 3 6, so 1 6 on top, and 4 over 6 here, which equals to 1 6 multiplied by 6 fourths, and we can cross out these numbers, and the answer here would be 1 quarter. And this is new probability for a person to be heterozygous. And in the column on the right we have 1 half divided by 1 half plus 1 6, and this would equal, as I said, this number plus this number, we should get 1, so this would equal to 3 quarters. So this is two new probabilities. This is a new probability that this person has this genetic disorder, and this is new probability that this person is homozygous normal and wouldn't develop this genetic disorder. So now we can choose the correct answer. Once again, we got 1 quarter here, and we got 3 quarters here. So probability that this person would develop this genetic disorder, and he would develop it if he inherited this dominant allele, would be 1 out of 4. And this is answer D. And our prior knowledge gave us information that his probability would be 1 half, because we know that father was affected, mother was not affected, so we can say that his probability is 1 half. But in the light of this conditional information or additional information, we corrected our probability, and as you see, final probability is much less than initial, and instead of 1 half, it is 1 in 4, or 25%. And this is all for today. Thank you for attention. Please subscribe for my new videos that I post almost every day. Thumbs up if you like this video. Please write your comments, questions if you have any, and see you in the next video. Goodbye.